Hey, what's going on, guys? For this question, I'll be solving Leetcode 207 course schedule, and this is a classic graph question that tests a bunch of different concepts that I think are super useful to know for interviewing. So let's just jump right into it. So the question gives you a scenario where you have, let's say, a number of courses that you have to take, and some of these courses might have prerequisites, and some of them might not have prerequisites. And the whole question is about figuring out whether you can finish the set of courses, as in taking all these courses with no issues. So you can think of it as if you're in college where you have to take 3 courses, 1, 2, 3, and you start with 1, and for you to be able to take 2, you need to take 1. So we'll just draw a diagram like this to be able to take 2. And to be able to take 3, you need to take 2. So we can just draw a diagram like this again. And that's essentially how it maps out if you were to visualize it. So let's say this is like just a 3-year program. So year 1 you have to take this, and year 2 you have to take 2, and year 3 you have to take 3, and it has to be in this order. Let's think of this. Let's look at this example. So they're giving us a prerequisite of 1, 0. That means you have to take 0 before taking 1. So you have to take 0 before taking 1, and also 0, 1, that means you have to take 1 before taking 0. So you end up in this weird state where if you want to take 0, you have to take course 1. But if you want to take course 1, you have to take course 0. So quickly, I hope you see this, how we're going to tackle this question. It's going to be essentially figuring out if, as we lay out this prerequisite graph, if we have a cycle somewhere in the graph. And if we do, that means that we cannot finish this course schedule. So let's see how we can actually translate this into code to figure out whether we have a cycle. And just to reiterate, that's going to be really the core concept of this question, is just figuring out whether you have a cycle in a graph. So just forget about, the way to approach it is just forget about this whole course schedule or whatnot. It's essentially you just have a graph and you want to figure out whether you have a cycle in it. That's going to be the meat of the algorithm. So let me just clear this. Okay, so I'm gonna assume we have the graph built out in a dictionary, and I won't spend a lot of time here, but just quickly glance it over once we jump to the coding part. But let's say we have the graph of that looks something like this. We'll start out with one that doesn't have a cycle, and then move on to one that does have a cycle. Okay, so just by looking at this, we know we need to take 1 before taking 2 or 3. And to take 4, we need to take 2 and 3. So how do you know if this has a cycle? Now let's say we're iterating the graph starting at 1. So we have this data stored somewhere, and as we know, we always store this in dictionaries, where the key is going to be the node and the value is going to be the vertices that it can go to. So this is really how this is going to look like in a dictionary format. And 4 goes to nothing, so this is going to be empty. So let's start with 1 here. I'm just going to bring up bunch of different colors, because the way I want to solve this is we're going to use different states when we're iterating the graph. So let's say when we start at 1 here, we're going to have different states. So 1 is called we're in the middle of processing, and 1 is called we're done. These are the 2 different states, and this is going to help us keep track of whether we have a cycle or not, and I'm going to show you how right now. So for processing, I'm just going to say that we're using the color red, and for done, for done, we'll just use red. And for processing, we'll use yellow for now. Okay, so once we start iterating the graph, we're going to start at 1. And right now, this doesn't have any state. It's neither yellow or red. So we're going to mark it as processing to begin our cycle, our algorithm of iterating this graph. So once we start at 1, we're going to look at what the neighbors are. We have 2 or 3. Let's just pick any one of them. We're going to do a depth first search. So we're going to go through each of the arrows for going to the neighbors. So in this case, we're going to go through 1 to 2 to 4 before going back to 3. And that's depth first search in a nutshell. So once we go to 2, we notice it doesn't have any state, so we're going to mark it as yellow. And once we're at 2, we check what the neighbors are. It's 4. So once we go to 4, we're going to mark it as yellow. And once we're at 4, we notice we have no more routes to traverse. And this is where we actually mark it as done. So it's at a red now. And then once it goes back to 2, we have no more neighbors to iterate, since we've already exhausted all the neighbors, which is 4. We're going to mark this as red. Now, once we go back to 1, we have still one more path to go through, and it's the 3. So we mark this as processing. Once we're at 3, we look at the only remaining neighbor. It's 4. We already seen that this is done. We already know that like we've taken all the prerequisites to get to this stage. So we don't need to bother by visiting 4. And we can short circuit this by just marking 3 as done. Since there's no more neighbors, it's all done now at this stage. So now if you notice, there's no cycle here. And we can kind of find this out by figuring out whether we looked at one node while it was in the processing stage. And that didn't happen in any part when we were traversing this graph. Now let me clear this and try to do this for a graph that does have a cycle and see what it looks like. Okay, now for this graph, we can obviously tell, like graphically we can see, visually we can see that there's a cycle. But let's go through that same algorithm that we went through. And we're just going to start off from the first node. And we've already built out the dictionary here, which stores the representation of this graph, the key being the vertex, and the values being the neighbors that it can go to. And I noticed that I did a mistake here. For 1, it only goes to 2. It doesn't go to 4. Okay, so now if we begin with the same process, when we start with 1, we mark it as this is in the middle of processing. So we can color it yellow. Then using depth first search, we go through each neighbor. So now we can see that we're at 2 here, or the only possible neighbor is 2. So we're going to mark 2 as processing and visit that. And from 2, we have either 3 or 4. Let me go to 4 first. So if we go to 4, we're going to be at 4 and we'll mark it as processing. And now from 4, the only possible way is to go to 3. So we'll mark 3 as being processing. Now from 3, we actually have one more place to go, which is back to 1. But now when we go back to 1, we notice that this is actually still being processed. So there's no way that we can finish this schedule since there's a cycle in the graph. If we want to take 2, we need to take 1. And if we want to take 3, we need to take 2. But if we want to take 3, we must also take 1, which makes no sense at this point. And that's how we can return from this function and return false to this whole algorithm, because there's a cycle that we found in the graph. I hope that made sense. Like, the tricky part is just figuring out how to traverse the graph using these 2 states. There are different ways to do it, but I found that using the states are a bit easier. And now I'll walk through the code and see what that looks like after we code it up. Okay, so I've gone ahead and coded the solution for this, just so I can talk through the code. I think it'll be easier for me to explain it that way. But initially, we can start out by checking if we have any prerequisites. If we don't have any prerequisites, then we can just take all the courses. It doesn't matter, since there's no requirement to take a course before any of the other courses. And then after that, we can just build out the graph using a dictionary, where it's the same format as we had previously, which looked like this. Whatever the course is that you have to take is the key, and the courses that go after it are the values. So to take 2, you need to take 1. That's how I interpret this dictionary. So given that our format is given like this, where the prerequisite is AI and BI for each entry in a prerequisite, it indicates you need to take B before you can take A. So this is going to be the source, which I marked here, and the destination is going to be A. And that's how we build the dictionary. And we can just ignore this section for now, because this is the function we're going to call. But once that's built, we can just go through each course, and if the course doesn't have if it's not a prerequisite to any of the other courses, for example, if we have this missing, so 3 is like kind of the final course, it's not a prerequisite to any other course, then we don't need to bother to iterate this or to call this function, since it's just going to be an empty paths that go from there, and we just continue. But otherwise, we can call this function, which does the depth first search, passing it in the vertex and the dictionary that we built for the graph. And this is where we introduce the 2 states of processing and done. And we first start by checking the state dictionary, whether we have this course in the state or not. If we don't, then we just mark it with any arbitrary number other than processing and done, which is 0 in this case. So I can just be like initial state is equal to 0. And we can just mark it as 0 here first. Otherwise, we can check if this course is being processed, then we return false, and that's where we indicate that we found a cycle. But if it's done, then we short circuit from there and we return true. These are all the final checks, but then the actual meat of the algorithm is we mark this course as being processed and then go through each course, like as in the neighboring vertices. So in this case, we go through, we're in 1, we marked it as processed, and we go through each course, which in this case it'd just be 2, and we call the function on it, passing in the graph and the current state. So the graph never changes. We don't modify that because that's going to be just the initial call down here with the dictionary. And let's forget this for loop for now, but once it goes through the very end where you don't have any more courses, you mark it as done and you return true. And that's the case where it makes it all the way to, in the first example, where it goes all the way to 3 or 4 when there's no more vertices to go to. We just mark it as done. We color it red. So here's where we check if any of the function returns false, i.e. caught a cycle, then we can just return right away from this depth first search, since there's no way that you'll be able to complete the courses. And we can check that where we call the function down here. So yeah, it's just using these like 3 states, initial state if you count it as one. It really helps visualizing how you're processing or how you're iterating the graph and figuring out if there's a cycle. I hope that made sense. If it might seem a bit tricky, but I think if you sit down and go through the steps, it's gonna add up pretty quickly. Let me know if there's any questions. Thanks for watching.